This brings us to our second topic of the day, which is the seismic load requirements for the components and claddings that we typically design for. So I'm going to try to show some important sections on the ASCE 7 that are relevant to this topic. For parts of the country in which there is seismic activity, like the West Coast, parts of the Mid-Atlantic region, regions near the eastern part of Arkansas and western part of Tennessee, and a few other pockets around the country, we have to consider the effects of the ground shaking. The main something that it has helped me a lot understanding and navigating around the area of seismic activity and seismic loads. The main difference between a seismic load and a wind load is that a seismic load is what we call an inertia type of load. It's not necessarily load like snow, wind, or ice that is applied onto an element. It's more of a inertia type load in the sense that when something moves, if the ground underneath your feet move and your shoes are bolted to the ground, you're going to try to resist that movement with the inertia of your body. That's, if you're taking anything out of this conversation today, that is perhaps the most important, the key difference between the other types of loads that we design for an earthquake load. Seismic loading is an inertia type loading, so the heavier the element that you're trying to restrain from moving, the larger the force that it's going to require to keep that element in place, installed. When the ground shakes, we don't want curtain wall or other equipment to be flying off the building. So that inertial load is what's causing our reaction loads. For the components that we typically design, we go to chapter 13 on the ASCE 7. And since we're making this video after the release and implementation of ASCE 722, I'm going to focus on this edition of the ASCE 7. The two major items that we use this chapter for are the seismic force, the FP value, which is what I was just describing a moment ago. And particular to our industry on glass and glazing is the glass fallout on curtain wall and glaze storefronts. I want to start this with the force, the seismic force portion of what we look at when we have a project that requires us to look into the seismic requirements. And real quick, what are the requirements? Sorry, let me put this sheet here. When are we exempt and where are we not exempt for the seismic requirements is listed at the beginning of chapter 13. There are some exclusions in which, for example, the component importance factor, not to be confused with the main force resisting system importance factor, if your component's importance factor is 1.0, meaning that none of these other sections apply, being a risk category 4, that the component is required to function for life safety purposes such as an egress or the staircases for the exit way of the building, or that the component holds any highly toxic or explosive substances. If any of these conditions don't apply, we are allowed to use an importance factor of 1. I've seen many times where the engineer mistakenly uses the seismic importance factor listed on the structural drawings. For our components, we need to be looking at this importance factor that is rarely, if ever, listed on the structural drawings. We look it up based on these exceptions here. And many times the when we have buildings that have an importance factor of 1 for the component importance factor of 1, and the building is located in seismic design categories A or B, which I'll show here in a little bit, where to find that and how to determine the seismic design category, that the code allows us to basically be exempt from any seismic requirements. So for places like Texas, Florida, some parts of the upper Midwest, Chicago, most of the structures will be sitting on a lot that has been determined to be on a seismic design category A or B, in which cases the components will not need to meet any of the seismic criteria. For the 722 version, the force that we need to take into account for our components is listed on section 13.3, and it has the form of this equation, FP. On the newest code, it's not 720, it's 720. There has been quite a bit of a revision from 710 through 716, which remained the same. You could see our spreadsheet was quite short in 710. In 716, they included this overstrength factor, which I'll briefly mention here in a second. And 722, the inputs that we need to look at for that FP value increase considerably, because we don't want what they call the whiplash effect, that the building resonates with the curtain wall, and that could amplify the reactions and the displacements greatly. So there is, on the 722, there is some inputs that we need to know for calculating that FP value. So on this equation 13.3 is redundancy factor. The code almost always allows us to use a redundancy factor of 1. This redundancy factor is mostly applied for main force resisting system. It deals with, okay, if you have one element that fails, does the entire system is going to collapse, or do you have other redundant ways to direct the load? For our practical purposes, this would almost always be 1, and it's allowed to be taken as 1 on the code. Spectral acceleration, this SDS value, comes from tabulated maps that are on chapter 12 based on the acceleration of the ground. And there is an equation on chapter 12 that, based on all this short and long duration, here, let me get to that equation. It's actually chapter 11 here. So that SDS value, the sine spectral response acceleration parameter, without getting too deep into it, considers the short and the 1 second ground acceleration based on the design earthquake, maximum considered earthquake at that location. So there's a whole forms that I don't want to open about how that is determined, but it takes into account the statistical history of the location and how many earthquakes have happened there, and what was the maximum ever recorded acceleration over the last so many years. So just note that your SDS on that equation tells you basically the parameters of what is the maximum amount of acceleration that we need to account for on that specific place. So this SDS value that is on the spreadsheet, I would say, if you're in a seismic area, by law, almost, the structural drawings need to specify what that SDS value is. So this value you gather from the structural drawings. Your overstrength factor, this is a factor that tells you that basically if you're connecting this element that you're designing into brittle material like concrete or CMU, this factor increases the load that you need to, the force, the FP, the equivalent seismic pressure that we'll show here in a minute. It increases it by a factor of 2. That factor is found on table 13.5.1, which can also be found on chapter 13. For different types of elements, we have different types of strength, overstrength factor. This is a huge change from 2010 and 2016, in which 2010 simply did not list any overstrength factor for our components. 2016 had a overstrength factor of 1 for the wall element of, say, a curtain wall, and 2016 they are including an overstrength factor of 2 for the wall element itself. And on this table 13.5.1, if we're dealing with an exterior curtain wall, we would look at this section of the table, because it's an exterior curtain wall considered an exterior non-structural wall element and connections. And this section of the table then takes us to the wall element itself and the fasteners of the connecting system. The overstrength factor, again, can have the impact of doubling your seismic force on the system. So 2016, they increased that considerably. Again, component importance factor, we discussed that briefly a moment ago, not to be confused with the seismic importance factor, IE value, which this value is typically shown on the structural drawings, but can also be found on table 1.52, the first chapter of ASCE 7. But again, this is for the main force resisting system. So on the 2022 spreadsheet, we made it very clear that these two are different. They're not the same, and you need to look for the IP on chapter 13 and the IE on most structural drawings will have it. The component operating weight, this is the weight of our curtain wall, or the weight of our storefront, or the panels, or the stone panels if we're hanging stone panels on the outside of the building. It is what you would typically use for your distributed dead load on your RISA models. We typically use 8 PSF for the combination of glass and aluminum. If you have thicker glass, then this will be, of course, a little bit heavier. And this is a key component of this equation. As you could see on the FP, the higher your WP, the higher your FP value.
Javier, just to ask a question about the operating weight, do you consider, like, after the fact, whenever you've reinforced it, go back and kind of take a look at that?
Absolutely. That's a great point. If you end up needing steel reinforcement on a curtain wall system, you most definitely need to include the weight of that steel reinforcement, which could increase it by 20 or 30%, and you will now have a much higher FP that you need to account. Like I said in the beginning, the heavier the element that you're trying to restrain, the higher your seismic forces. So yes, Stuart, that's a good point. Another factor that plays a big role on the amount of force that you're determining is how high on the building your element is. Of course, if you are closer to the top of the building on a very high building, the amount of acceleration that you will experience is a lot higher than if you're on a lower ground. If you're on the 12-story building and an earthquake hits, you're going to feel that movement and that acceleration a lot more than if you're in the ground floor. So this point of attachment, if you have multiple frames, I've also taken the approach of, okay, here's my highest anchor on the entire job. I'll use that height as my Z value. And of course, the average roof height will be the same for all the frames. But there is a little, most projects you would be okay just taking the highest point of attachment. Down here, I'm not going to get too deep into this, the fundamental period of the building, because the code does allow you, if for whatever reason this fundamental period is not known, and it also has to be the lowest fundamental period, meaning how the slow motion of a building, basically how many cycles per second, that gives you your period, how many cycles of vibration you have per 1 second. It gets into more on the behavior of the main building, and the code does allow us to say no, that we don't, and it forces the equations to a default value. So this is beyond the scope of this video, but we did include that in cases because sometimes you can reduce your FP value by some percentages. So we included this in the table as an option to say yes or no. And this has the effect on this amplification factor HF, which takes into account the height of the building and also fundamental period of the building. Response modification factor, this R value basically tells us how redundant our components are. If you have an element that, for a seismic situation, an unreinforced masonry wall will have a very low R value, whereas a moment frame that has been seismically detailed to yield will have a very high R value. So just know that this R value here on this equation, the higher the R value is, the lower your FP value needs to be, because it's in the denominator of this equation, so it'll have that impact on the FP. When you have an element that if it fails, it can potentially fail catastrophically, your R value is going to be smaller, which will increase your FP value. And that applies for the main force resisting system, but also for the component that we're looking, resisting systems R value. The component resonance ductility also involves the ability to deflect, how ductile or brittle the component that we're dealing with is. Typically, if you're anchoring into a concrete substrate or a CMU substrate, this CAR value is going to be larger. But if you are dealing with a very ductile element that can deflect a lot before failure, the CAR value will be slightly smaller. After you gather all of these values from chapter 13 and beyond, also chapter 12, you have all the ingredients basically to calculate your FP value. It is worth noting here that the code allows a range of these values. It doesn't want you to, the code doesn't allow you or want you to go above this FP maximum, which is, it caps it at 1.6 SDS times your importance factors and the weight of this element, and also has a minimum requirement of 0.3. So the equation is the same. What changes is that 1.6 and that 0.3. So if your FP value based on this is lower or higher than this, the equation that our spreadsheet basically truncates that and spits out the governing FP value. On the equation, we included this overstrength factor down here because that's basically how overstrength factors are applied. They're applied to the final equation, not necessarily to the minimums and maximums. So that's why in this case, I believe we had a 2 for our strength factor. If you multiply 2.96 times that 2 is, we get that 5.9. A big change that came on 722, and this is going to be interesting to see how creative we get on applying this type of load. The code now requires us to apply this FP value in 2 horizontal directions, basically case 1 and case 2. Section 13.3.1, which I believe we have a copy here. 13.3.1. If not, I can pull it up on the code. But it tells us that we need to apply, let me open up the code. It tells us that we need to apply the full force of this FP value in one direction and then also combine it with an orthogonal direction, but only 30% of that force. So we could just be conservative and apply this load, find the resultant load, and apply it that way to our F&T anchors. 13.3. Okay, so if you see here, the direction of FP use shall be those that produce the most critical load effects on the component supports and attachments. Alternatively, it is permitted to use the more severe of the following two load cases. A combination of 100% of FP in any one horizontal direction and 30% of FP in a perpendicular direction applied simultaneously, or the combinations from case 1 rotated 90 degrees. So they're basically saying the same, but now we need to consider the full-on force of the seismic loading, and then also include a 30% of that load on the orthogonal direction, perpendicular horizontal directions. Again, this is something that's fairly new on this for us, so we'll have to find creative ways in which we do either like a biaxial check on our emollients if the loads are high enough. We can also call it okay by comparison if we know that we have a very high wind load that it has only stressed our emollient to 50%, for example, and our FP values are small. We can make a case on how this lower pressure will be okay by comparison. So again, it's one of the bigger changes that I've seen is the requirement for the code now to apply this load in two directions. And there's also this one additional load that we need to take into account, which is the concurrent vertical force load. It's basically whenever the ground shakes and the structure bounces up and down, there is a provision on the code, which is a much simpler equation. 0.2 times your spectral acceleration times the weight of your system. This will come into play whenever you're dead loading a curtain wall out of a slab, and like Stuart said, you end up having to reinforce your curtain wall. We do need to take into account that if the ground shakes, that curtain wall might bounce up and down. So that is how the new spreadsheet has implemented the requirements of 2022 ASCE. And the other topic that I wanted to show is the glass fallout spreadsheet that we have developed, and it's still under one final round of reviews. But basically this is the spreadsheet here that tells us if the glass in our curtain wall can sustain the drift of the building without failure. We put together this flow chart at the beginning of the spreadsheet. It says in big red letters, says read first, and it gives you a good roadmap of how to take this requirement into account. You start with looking at your seismic design category. Seismic design categories A or B typically will not require us to check for delta fallout. We would be exempt from this requirement as long as we're not in a risk category 4, such as a hospital or essential facility. If you're in a risk category 4, every piece of glass on the building needs to be validated for this delta fallout. If you're in seismic design category C, D, E, or F, regardless of your risk category, we do need to take this into account. If the manufacturer has seismic test reports, we need to take a look at the seismic test reports and see if the system that we're using has been tested to accommodate this much movement. If we verify that and actually I will share this little video that I have for, give me one second. This is a video of what a typical racking test entails, and you could see that the frames are moved laterally with hydraulic jacks, trying to mimic what a curtain wall will experience during a seismic load. You can see here the curtain wall might be attached with a wind load clip to a floor slab, and then might be attached to the roof there. And what this type of test, the AMA 501.6 test, try to do is come up with a value of drift that the curtain wall can safely accommodate without glass breakage. So there's every big manufacturing company has tested their captured system as and I say captured because for an SSG system, the only way we have to validate system is through testing. So following on the flow chart here, the frame has the same booleans.
Can you increase the size just slightly?
Yes.
Yeah, there you go.
If the mullions and the sizes of the DLO of the tested frame have the same sizes and mullions and everything that we do in our project, we can use the testing of that system to validate our project. Even if our DLOs are slightly smaller and our heights are smaller, we can still validate the project using that delta, the testing that the manufacturer has put together. If we find that the system has not been tested, or that the mullions are not the same as what have been tested, and or the DLOs are larger than what have been tested, we're forced to use the spreadsheet that we have put together. If after you put all your inputs on the spreadsheet, you see no flags, all your DLOs work okay, then the delta fallout requirement has been validated. If any of the frames have a no good flag, we need to look into the exceptions. ASCE 713591 is the section of the code that covers glass on curtain walls, and they have exceptions for when this delta fallout is not required or can be. If all else fails, we've come up with a way in which we can back calculate the amount of drift from a tested frame and compare it to our project frame. This is a trick that we came up with. We validated this with a structural engineer here in California many years ago. I believe he was part of the Chapter 13 committee that worked on this delta fallout, and we asked him, if we do this back calculation, if we know the system but our project has larger DLOs, could we find the amount of drift that the frame was tested on and back calculate what that much deflection of the tested frame would have cost to our frame? And if you ever get to this point, please talk to me and I can walk you through the steps. I don't want to get lost in the weeds about this, but there is a trick way to back calculate the amount that was tested for our frames. If all else fails and we can validate it and we don't fall within the exceptions, we are forced to send the EOR and RFI asking to provide us the actual drift capacity or the actual drift on that location of the building. Many times the allowable drift that we use is based out of table on chapter 12 that tells us, okay, this building is either a masonry building or a steel frame or whatever, you can deflect 2% of your story height. Many times our curtain walls are in a corner of a building that might be a lot stiffer than the rest of the building, so we send an engineer on record an RFI asking them, hey, can you provide us the seismic drift for this location of the building? And I have seen times where the EOR comes back and says, yeah, there's a pretty stiff wall on that section, so our seismic drift on that location won't be as much as the 2% that you're using somewhere else. If that comes back and they tell us, no, it's the 2% and we can't really reduce that drift, then we have a problem. Then we need to tell the client, your pieces of glass are too big, you need an additional vertical mullion here or there to break your pieces of glass into smaller sections. So as you can see, it's a long road before we get to that point, and we have many outings before we get to that point. And I want to share the spreadsheet. As you can see, we're still on the final steps of validating the spreadsheet, and Kyle, Ben, and I have been working on implementing some of the things that were found, but it's almost in a final form. I don't expect many things to change. And this is basically what the spreadsheet looks like. It has a format of a summary sheet in which you get to put your clearances and your bites around the glass. And I'm gonna share my screen view. new window. So these values that you input here, the values that you input on the glass bite and the clearance values are dependent on each system and each mullions, and they're described on ASCE 7, but we included a tab here on the spreadsheet. It's the last tab where we show how these bites and clearance values need to be accounted for. The bite is how much space is the IGU being captured into your capture system, and your clearance is the distance between your IGU and your aluminum, either tongue of the mullion, or in the cases of a storefront, sometimes a thermal break will be in the way, as some of those thermal breaks eat into the glazing pocket a little bit. So that's something to really look out for if you have a thermally broken storefront mullion. Sometimes that thermal break really eats up into the glazing pocket, leaving a much smaller clearance. This newer spreadsheet on 2022 allows you to explore these exceptions, and I want to briefly show that exception on the code. Basically, on 1359, they tell you that if your piece of glass that you're trying to validate, 1359 is the section where you go for validating the glass in glazed curtain wall, glazed storefronts, and glazed partitions. This delta fallout and this DPL, all of those equations are implemented into that summary sheet. And for the exceptions, this first exception is something that we calculate in the spreadsheet, and this is something that Gorney and Ben brought up recently, that before we weren't treating this declear greater than 25 DPL as an exception. We were just treating it as part of the check. But if your declear ends up being larger than this 1.25 DPL, then you're exempt from it. Another exception, the second and third exception, they're more related to where the glass is located on the building. The full premise of this glass fallout requirement is that if there's an earthquake, you don't want glass falling, cascading down, raining down on people as they're trying to exit the building, or if there's someone near a building walking on the street and an earthquake hits. You don't want falling glass, which has been known to cause a lot of damage. And I have a couple of pictures here of this. Was on an old building in San Francisco that experienced some seismic activity, and the glass broke and it injured some people inside the building as well as outside. And so we're trying to make sure that when the building racks and moves, glass is not going to become a falling hazard to people inside or outside of the building. So the second exception here for us to be exempt is fully tempered monolithic glass in risk categories 1, 2, and 3, located no more than 10 feet above a walking surface, need not comply with this requirement. And there's also the third exception that basically says that if you laminate your glass and it's captured mechanically, so we have a captured curtain wall system, and is wet glazed, and the perimeter is secured by a frame with a gunnable curing elastometric sealant perimeter bed of 1/2 inch, basically they would have to wet glaze the perimeter of the glass. Again, trying to, if the glass breaks, is the wet sealant is going to keep it in place, and the interlayer is going to keep the glass in place as well. If those two exceptions apply, then we would be exempt from this delta fallout requirement. So on column D, we
Javier,
yes.
Javier, quickly show on the sketches, wet glazed versus a just dry glazed.
Yes. So here on the sketches, you have a system that has been captured mechanically, and you see here there's a setting block. You have basically air here, an air pocket between the glass and the glazing tongue. the mullion tongue. For a wet glaze application, what they do is they capture the system using this pressure plate, and they fill this air void, with a structural silicone. And
Not exactly just part of that gasket is eliminated, and then a structural silicone is filled into that gasket area.
They would fill part of the sealant would also make its way in between the glass and the pocket.
Over the top of the insulated glass and through the side?
I believe so, yes. So it's basically a difference between only capturing the glass with your pressure plate, with now having a silicone glue that holds the glass in place. And so we're saying, instead of this rubber gasket that has this bearing pressure between the glass and the plate, you fill this gap here with a silicone that is glued, that basically glues the glass to the structure. And Stuart, I believe that there is some verbiage there that they require this to hold the edge of the glass as well, to prevent from falling from the frame. But that's a good thing to add to this diagrams.
For laminated glass that we're talking about, the wet glaze.
I think it's the exterior, because you're trying to prevent fallout on that exterior ply.
But
So
aren't they talking about laminated glass though?
You gotta do it.
They do.
So hurricane, the laminated glass is on the end, is what we're worried about.
It's not that they were.
it would fall inside the building.
Okay,
Yeah.
Javier, can you go
Okay.
back to that?
Because there's a
laminated.
laminated.
Are they talking about it?
I always took that exclusion as it can't be a laminated IGU.
Laminated on the outboard side is a special glass, so that.
I thought I thought they were just saying a laminated.
Oh,
Yeah,
I have glass, not an
that'd be
IG.
better.
that's what I thought too. I didn't
Because then
apply to
then
laminated
you,
IGUs.
it's just
Yeah.
the glass being adhered to the main portion of the mullions. Since it's laminated, nothing's gonna fall off the.
I think that's
One
actually-
solution, one
But yeah,
solution that we've
IGU.
used, one solution that we used in the past is asking the client to keep the IGU, but only laminate the outboard. And there was a case that we had to laminate the inboard because these pieces of glass were above a staircase, really high up. So if the ground shook and the glass broke, it could fall inside the building as well. So the 10 feet above walking surface applies both outside and inside.
Yeah, that's what I was gonna say. You gotta use the
Yeah.
engineering measurement, 10 feet
Yeah.
walking surface.
So that's a good idea to add maybe an image of a wet seal or a wet glaze detail there. And maybe Russell, if you have in your inventory, if you have seen a wet glaze detail for a curtain wall, maybe you can share that with me and we can throw that in the spreadsheet.
Yeah, I've never seen that on a curtain wall. I've wet glazed a bunch of vents and stuff like that, but I haven't seen that on the curtain wall, but I'm sure I can find something.
Okay, all right. So the spreadsheet has this exception, it does exception 2 on 13.5.1 apply. This is basically the 10 foot over walking surface. Because if it does, then basically the spreadsheet tells you, okay, no, you're exempt. As you move to the right, in case you say no to this exemption, then you put in your DLO heights and DLO widths. This setting block also will matter, and because you have the option between quarter point and eighth point. And just for brevity, and not to make this video too long, this whole declear equation and fallout equation is based on paper from Bukamp and Michan back in the 60s, in which they tested frame sachet of wood, and the glass was continuously supported by this elastometric rubber on the bottom. So that's very different from what we see in the typical applications of having the glass supported by 2 setting blocks. So this declear equation is somewhat misleading on the way the glass is supported, but because of the efforts that we've had in JI and the brilliant minds that work together, we found a way to justify the rotation of the glass with respect to the setting block instead of having a continuously supported bottom edge of glass. So this column G allows the spreadsheet to calculate this, and I'm going to borrow Kyle's diagram here. The glass will rotate along the edge of the setting block, and then the spreadsheet takes that drop of the glass into account in our calculations. And then let's see, the equations from columns H through M calculate all these other requirements for your DPL, your declear. Just know that the delta fallout is the capacity of your curtain wall to accommodate movement, and your DP value is the demand, basically how much movement is the building going to see. This allowable drift and the importance factor you gathered from table 12.2.1. This table is for the main force resisting system, and it varies based on the type of structure that you're building. And of course, the importance factor, the IE, that's also from the table 1.5, is not a component importance factor. It's the main force resisting system importance factor. So basically here what we're trying to do on column N is we're checking to see if that first exception on chapter 13 is met. If your declear is larger than 1.25 dp, then you're good, basically you're exempt. And that declear, this equation of HP times C2, BP times C1, all this comes from that paper from the 60s that I was mentioning before, and that this is dependent on the type of mullion and the clearances that you have on each side. And as you could see here, C1 is the average of the clearance on both sides between the vertical glass edges and the frame, and C2 is average of the clearances at the top and bottom between the horizontal glass and the glass frame. So this is highly dependent on the type of mullions that you have, and you might need a couple of spreadsheets if you have different mullions that have different clearances. You can just group the frames into the mullions that apply to each one, and maybe have one or two spreadsheets, that summary spreadsheets that do this check for you. And then the HP and the BP are basically the height of your glass, and it takes into account that the glass will have a bite of 1/2 inch. So you have your DLO dimension, and then you have to add to that your top and bottom and your left and right bite. This HP value takes that into account. If you can see the equation, it takes your DLO height and it adds your bite top and bottom. Same with your width, your BP. It takes your DLO width and adds your left and right bite into the equation. So after you fill in all your values and you make sure that you're applying the exceptions and if we can be exempt, that's great. If not, we really need to take a look into the sizes of the glass. And remember, we have many ways of getting the system to work based on this read first flow chart. So if for whatever reason you end up having a flag of no good here, refer back to this read first to see where are you falling on this flow chart, and also reach to your team, reach out to me to see ways in which we can put together an RFI for the EOR to help us try to meet this glass fallout requirement. So again, this is a high-level introduction onto this topic. There's a few intricacies that we would need to spend a whole other hour discussing for all the seismic requirements that we have, but this video was intended to give the group a quick crash course on these two spreadsheets that we have developed. I think we can have a few minutes with questions or comments from anyone. The floor is open.
I have a question.
Yes.
Because I remember when I was doing the high-rise buildings, when it comes to, let's say, same with the dead load clip and the wind load clip, you have mentioned that in the curtain wall area, it says wall element, it says frames, anchors and connections, FP. So under the anchors and connections, you have this values like to calculate for the seismic load that needs to be applied. So when I was applying the loads, I have a load of facing the glass wind load, I have the dead load, and I have a lateral load. That lateral load is coming from the FP given for the connections in that seismic table that you provided. So it is also calculated. So I don't see that FP load that we are applying on connections, like anchors and connections for what load are we applying? If, let's say, it is in Illinois, which is the
I think-
seismic.
Aren't the values, because you're talking about where for the wall, it's one,
Yeah.
one, one, one,
This
and
is
then you
for
have
the-
two something, two something. Can you go to that table?
Yes. And Ivy, while I look at this table, the previous sheet had a little drop-down menu
Yeah, there you
a drop-down menu that allowed you to select the body of the element or the anchor of the element. But now the spreadsheet has it baked in that if you're doing this for the wall element, you have to use these values. If you use this for the fasteners, you use these other values.
Hey,
And-
Javier.
Yes.
Which would spit, if we're looking at the wall element compared to the fasteners, which spits out the higher?
So it would be the fasteners, yes.
Okay.
You'll need to run two spreadsheets if you're analyzing a wall and the anchors, because there can be different equivalent seismic pressures for both.
Yes.
And then you can
yes.
just compare them both to the wind load, essentially.
To the wind load with,
And research just running another load combination.
but Ben, remember that this case threw a wrench to our comparison because now it's asking us to consider an like a perpendicular load of 30%. So we can get creative on how to validate that. And if we have plenty of capacity on an anchor or a mullion, I would be okay calling it okay by observation or comparison. But there are many times that this could push us over. And Ivy brings a good point that I want to touch on and briefly discuss. How do you apply that FP value? Basically the same as you would, it's an equivalent lateral pressure. You apply it very similarly as you would a wind load pressure. So if you have a mullion that, for example, this mullion, you would apply that FP value along the tributary width of that one mullion. I'm going to make this green. It's very similar that you would a wind load along the trib width of that mullion. And for your anchors, say you're designing your seismic load for that anchor above there, similar to wind load, you would take your tributary pressure, equivalent lateral pressure, and apply it to that wind load anchor. The same with your sill. If you have a mid-span anchor somewhere here, you would also just apply it based on your tributary area for that component. So yeah, Ivy, thanks for
I just
bringing that up.
brought it up because you showed that video. So whenever you do that testing, like bracket, definitely your bracket will have a lateral load, like horizontal. So it's a FY, FX, and FC. So that's why I asked, because whenever I'm doing that in the analysis before, doing the horizontal, I'm using the values for the anchors, which will give me also higher seismic load.
We are doing it, but most of the time it's just by inspection. You're saying is we don't actually run them.
But by inspection, you mean you have dead load and this, but this is a
lateral.
And
That's what-
Ivy, also look the CAR value, which is this component's resonance ductility factor. For your fasteners of the connecting system, you jump to 2.8. For the wall element is 1. And you could see here on the equation of FP, CAR is a numerator. So the higher the CAR, the higher your FP value will be. So fasteners are less, how should I call it? An aluminum frame can deflect more, the curtain wall can deflect more before failure. Or your anchor, if the bolt goes, it goes. There's not much redundancy on that connection. So I think that's the premise why you have that higher value of 2.8.
But what about the omega factor? Have you scrolled?
That's always 2.
It's 2 for the body and
on
for the frame.
722. Yeah, so on 722, oh yeah, you're right. It went down to 1. I think they made that up with the higher 2.8 value. And there's always look at the footnotes. The devil is always on the footnotes. It says that overstrength factor will require for non-ductile anchorage to concrete and masonry. So many times you would have to, if you're anchoring into concrete, you need to pay attention to what is being said. 13.44. When it is required to apply the seismic load effects included in overstrength section 12.43, delta L shall be taken as the anchorage overstrength factor given in these tables. So it's kind of like a loop around between then and there. But I will say one last thing about this overstrength factor. We focused this conversation for curtain wall elements. Whenever you have guardrails that are on seismic areas that are anchoring to concrete, do pay attention to this section of cantilever elements unbraced below its center of mass. Parapets and cantilever interior non-structural walls, they will have an overstrength factor of 1.75, and this can mean increasing your reaction loads on your Hilti profis by 75%. So that can have a really big impact on your connection to concrete. To Ivy's point also on the connection, so say we have a wind load clip. I'm gonna use this project, we haven't sealed it yet, but so whenever we have a wind load clip like this, of course, wind load in this direction will almost always govern. But on the perpendicular direction here, we need to take that into account, because if this angle extends, say 18 inches or 2 foot, sometimes these beams are way back there, that will really start causing some overturning and some really high stresses on the weld. And this clip might also start failing, because typically we use a 1/4 inch thick bent steel plate. It won't take much for that to bend over and fail. So it's wind load clips and dead load clips are something that we need to take a close look and apply this load in the direction that causes the worst load effect.
That's a load combination that should be considered, I guess, is the point. Whenever we've got some seismic loads that they're,
You don't combine, you combine dead load plus seismic or dead load plus wind. But my concern is that when you have this lateral load, means you are bending your plate in the weak direction.
Yeah.
Fail at the.
And it's definitely something we all should be familiar with. Maybe not Renice yet, but we should already be doing that when we have a curtain wall wrapping around a corner. Looking at the weak axis bending in those, essentially a plate, a bend plate.
And to Ivy's point, section 245 on the ASCE has a combination of dead and the earthquake load effects in the vertical direction and the horizontal direction. And the only other loads that are combined with seismic loads are live loads. So if you have a guardrail, you need to account for 75% of the load of people leaning on the guardrail whenever an earthquake hits. But even then, they're reducing, because of the probability of that happening, they're reducing that to 52% of your earthquake load. So you would apply that 52% to the FP value.
You don't need to do that for a guardrail, though.
Yeah, we do.
People leaning on the rail,
Before the earthquake starts, so they don't know.
it's similar to the live load wind. No?
I mean, with the live load wind, if people see a storm coming, they're going to take shelter. With an earthquake, you don't know it's coming. Of course, we wouldn't apply the 200-pound load, for sure. But leaves it up to discretion that we might need to apply the 50 pound per linear foot load, so that if people are like leaning on a glass veranda or like a glass guardrail and an earthquake hits, that we'd still have the capacity to hold, and then people are going to leave, or people are trying to leave and like leaning on the glass to hold while the earthquake is hitting. I wouldn't apply the 200 pound load.
Because during an earthquake, somebody could easily lose their balance and fall into it. So can you justify
Yes.
why you wouldn't look at the 200-pound load?
Just it would be a very unlucky day, but yeah, no, not really. The 50 pound per linear foot,
I would not look at the 200-pound load in that combination. Because they're
Yeah.
probably going to kick it back knowing your California inspectors that you've been dealing with on projects.
yeah, and it's
only-
that's a tricky one, but
Yeah, the only thing that I could add to that is that live load impact versus live load in the code is a little bit different. And so I'm not sure if that actually applies to impact type of live load, because it is distinguished in the code whenever we have impact loads.
and also Stuart,
And there may be some justification there to
Are we getting,
not over design
so that,
rate.
that's
Yeah.
why also with a 50 pounds per linear foot applied in any direction,
Yeah.
do you not need to take that additional weight into account at the top of the rail with seismic? Does it-
no, because
I mean-
seismic loads, if the component is not bolted, but here's the thing, and a good answer for that question is if you have an attic and you put a bunch of heavy boxes on the attic, that even partitions in the office, if it's not securely positively bolted to the structure, we don't consider that a seismic weight because it can float around. So it needs to be positively attached and mechanically attached to your components to add for the seismic weight.
Makes sense.
Laying over the top of the railing or holding on.
You're like holding
I'm
for
buckled
dear
on.
life on the railing.
One of
Maybe.
it says that 50-pound per foot should be applied in any direction.
I agree with Stuart that the impact load, I mean, you would have to be the moment of impact matching the maximal spectral acceleration of the ground shaking at that very same time. That's what it would create. Because an earthquake happens over 30 seconds, 60 seconds, it goes up and down. It would be incredibly unlikely that they coincide with an impact. With a 50 pound per linear foot, that's more of a minute. So people could be leaning there longer. The earthquake hits and they're like, oh no, what do we do? So I would be okay not considering the 200 pound load because it very unlikely it will coincide with the maximum acceleration. But open for discussion, open for debate. This leaves it up to the discretion of the ceiling engineer. Anyways, I know that's a lot. This meeting has reached the 2-hour mark, so I think it's a good time to wrap up unless somebody else has another comment or any questions on this.
I have one small thing. I've worked with Matt Gorney in a project that I use wet glaze. So it's this one I'm sharing right now. It's wet glaze in here using silicone. So they use silicone sealant. Just for letting you know.
But is it on the outside too, on the pressure plate?
It's shown in the inside section, and in the outside they're using just this tool.
But they don't have
Yeah,
insulated.
that's what I was talking about, where it's laminated, nothing's gonna fall off.
Yeah.
Yeah.
So they're
Okay.
using silicone in here. So for the delta fallout, perhaps Russell can include this markup, or we can include this markup because this is for impact resistant system.
Would
Okay.
they email that over to me and I'll put that to the other detail. And it looks like they have some foam glazing tape. They have that glass sitting on and then they seal the outside edge with the silicone.
All right. Thanks for sharing that, Juan Pablo. Thanks, everybody. Meeting adjourned.